Alright, this video is going to teach you about rolling and friction. Before we had done with boxes, that was sliding friction. Now we're dealing with rolling friction. So the first question asks, what happens if you push with no friction? So let's say you have a force applied and you push at the bottom. Right? So what happens if I push here? Right? Well, with the blue, right, the object will move to the right. Right? So its linear motion will be to the right. Right? Then it will rotate. Let's say the axis of rotation is in the center. So that is going to cause it to rotate this direction. So that is going to rotate counterclockwise. Alright, let's change this up a little bit. Now what's going to happen if you pushed with a force applied, so I'm just changing the color so we can see this, if you pushed here at the center. Right? Again, linear motion doesn't matter where you push it. It's always going to do the same thing. If I push at the bottom or I push in the middle, it's still going to move to the right. Or I guess I should say it's going to accelerate to the right. Okay. Now if I push in the middle, that force line goes through the axis of rotation, so there'll be no rotation. Okay. Let's do one more. Okay. What happens if I force applied? Okay. If I push at the top of this ball? So I push at the top of this one, again it's going to accelerate to the right. Now that's a linear acceleration. And then it is going to rotate clockwise. So there you're going to have an angular acceleration clockwise. If I went back into this one, this is going to have, it's going to rotate and have an angular acceleration counterclockwise. Okay. So now what we need to do is figure out what is the purpose of rolling friction. So the purpose of rolling friction here is that an object or a rolling object will not slip. Now, another thing that we call this is we end up with an equation to help us that is called the non-slip equation. It's going to help describe all of this. Non-slip equation. That equation is alpha times r equals a. Okay. Now let's take a look here though and see what slipping looks like. Okay. Well, if I look at this example here, I'm going to have this object. Okay. I'm going to have a cue ball. Okay. And as we go and see, okay, this one on the right, okay, it's just accelerating to the right, but it is not rotating. Okay. If I look over here at the ball on the left, okay, the ball on the left is rotating but not moving to the right. Now it's starting to rotate. So this is non-slip, where you're rotating to the right and you are having some angular acceleration to the right. Let's go back and double check this again. So here we have this one come. If we look at the left, okay, here we have it rotating to the right but not moving to the right. So that is slipping. So we're going to be talking about this a lot in class, but this is what's happening. Okay. How it's working from this equation, okay, if we were to look at this, okay, is these two equations aren't equal. Right? So if I were to go back to the first one, the red one here, okay, and I was looking at the equation, alpha times r is supposed to equal a. Okay. Now in the first one, if I'm moving to the right, okay, I have an a linear acceleration to the right, so we'll call that a positive number. Okay. Now, it's rotating counterclockwise, right? But that's the opposite direction. For this equation to be balanced, they both have to have the same sign. So then this side would be a negative. Right? So this is not going to be equal. One is negative and one is positive. So what we end up with in this scenario is that the linear acceleration is greater than the angular acceleration because the angular acceleration is negative. So what has to happen is friction will fix the slipping. So friction is going to balance out this equation. So what could friction do? Well, this number over here is too big. So friction is going to make that number smaller. Now, let me erase some things and zoom in to look at the diagram real fast. So back to this diagram. Okay, I can see alpha times r is less than acceleration, but they need to be equal to each other. So friction, which I'm going to put in blue, has to fix that. Okay? So the linear acceleration is going to the right in this diagram of this rolling ball because I only have one net force. Okay, or one force, so that's my net force is going to the right. So then friction is going to fix this. Friction is going to fix it, right? And friction will make that acceleration smaller. So which way would I go? Would I go to the right or to the left from this dot? Well, I would go to the left. So friction would go to the right. So then this would go down. So then eventually it could be equal to the other side. Now, there's a cool purpose. Friction actually does a dual purpose. Because friction, we just saw, it decreased the acceleration, which is too big. But what also happens? Well, if I look here, there's my axis of rotation. Friction is now going to give me a clockwise torque to balance out the counterclockwise torque from the force applied. So friction is going to make this bigger and also make this smaller. So eventually they're going to balance out and be equal. And so that's the whole purpose of friction, is to balance out the non-slip equation. So it's what's going to happen is sometimes this side will be bigger, so friction will decrease that and increase this. Or if we looked at another scenario, right, where the angular acceleration is too big, then friction will decrease that and increase this. Okay. Let's try that. Let's go back and look at one of our original examples again, okay, and see that one. So let's look at this one. Right? In this one, in the blue one, we pushed right here at the center, and we said it moves or accelerates to the right but has no rotation. So if I accelerate to the right, this is going to be positive, and this side is 0. Well, this ends up with the same thing, that I end up with a positive is greater than a 0, so then I have to slow down the linear acceleration or speed up the angular acceleration in the clockwise direction. So that case, you would have friction going this direction. That gives you your clockwise torque. That also changes your net force. Before it was just to the right. Now I have a net force that also tries to cancel out some of that rightward force, so that balances this equation out. Let me pause it again and let's do the last one here in green. So this last example, again, what happens if you push at the top? Well, in this example, right, we see my green writing there. It accelerates to the right and it rotates counterclockwise. So if these two, they could be balanced, right? The alpha, which I see here, the alpha could be balanced, so I could be fine. Okay? But what happens if you push way too hard and it rotates too much? That was like this example. Right? Let's see if I can get this one going. So here, right, the ball on the left, you notice it comes in. Okay? This is rotating to the right, but not moving to the right. So what's going to happen on this one? Well, maybe you noticed it slowed down the rotation. So pause it and think, what could have caused that? Right? Again, our only forces are touching forces. So let's say In this one, it was rotating faster than it was moving to the right. So our equation now has changed. And this side is greater. This is also called topspin. Okay. So this side is greater. So I can do two things. Right? This is now less, so I can increase the linear acceleration and decrease the angular acceleration. How can I increase the linear acceleration to the right? Well, I can push harder. So here, friction is going to go forward. Right? This is how a car works. Right? If you spin your tires too much, it's going to be pushing you forward. So friction actually helps you, and we'll look at lots of examples with this. Friction then is going to put a counterclockwise torque, right, that's supposed to be an arrow, to cancel out the clockwise torque from the force applied, so it's dropping this down.